particular about college football?
No.
No, she is.
No,
No, from the like 1930s.
Oh.
It's all black and white.
And they act like they are acting limbs, although they're like mice, although they are sound. Because they don't. Like, they act like they're in the theater instead of in the movie.
Oh, the Marx Brothers originally were in what's called vaudeville, which was early. There was a whole circuit, and they travel. They travel around in different places, put on shows in different towns, and then they actually did Broadway musicals that were because they thought like the regular musicals. They were amused by them. So they were kind of parodies. So one of the first movies, Animal Crackers, was actually a Broadway show.
I have no idea what you're talking about.
Marx Brothers movies.
Well, now I gotta move my bag.
Now you know.
Now
I'm not even touching your bag.
How come
I have to show you the mirror scene.
everybody pronounces Chico's name
I'm
wrong?
showing you that. I
I
can't
don't
reach
know.
that.
It's too close.
You can't even reach that.
People pronounce it Chico, but
Right.
it's Chico.
It's Chico, you know why they call him that, right? He didn't even look like the type, did he?
No.
It's an attitude.
You know how some people are charismatic,
Right.
some people are Chico.
Yeah. Does he have a book out? I want to read it.
I don't think so.
I'm just teasing.
Alex, are you ready?
Ready to go, Mark.
All right. Okay, welcome everyone to the Tools and Technology Seminar Series. I just sent around the sign-in sheet, so as always, please remember to sign in to help us with the pizza. Hopefully you saw in the promotional emails, and I think I mentioned this a few weeks ago, but next week's speaker, October 26th and November 2nd, I think those are the dates. There was a swap in the speakers from the original schedule, so just in case you're interested in just one of those, make note of who's actually speaking next week. So today's speaker is Brent Griffin, and he is Assistant Research Scientist in Electrical Engineering and Computer Science, and his research interests are actually in robotics and computer vision.
All right, thank you. Well, thank you for having me here. It's an honor to speak for the Tools and Technology talk. And today I'm going to be talking about tools for volumetric segmentation and grouping. And I'm going to have several applications that I'm going to show you this method being applied to. But thanks to some colleagues of mine, Professor Jason Corso and Dr. Tom Yan, who's a postdoc in our lab, I'm going to be able to show you some applications that actually have to deal with medical imaging directly, as well as some other medical applications. And so while I've done a lot of computer vision type work in this kind of scenario, I haven't personally done any research in the medical imaging field. So if you have questions on these slides, I'll do my best to answer. But my hope is to at least kind of advertise to you things that have been done by colleagues from North Campus. And if you're more interested, we can talk after the seminar, and I can make sure you can get in contact with the right people if I can't answer questions that you have. And just kind of as a brief intro to this idea of segmentation, you see here, there's this brain. You have some initial imaging. Now you can do a manual annotation of this if you were looking for a tumor. But the goal of doing some segmentation of a volume, so you can actually turn these images, even if there are lots of slices, into a graph that's all interconnected, pixel to pixel, frame to frame. And this has applications in like a volume, in the case of an MRI, where you have actual frames lining up in slices in 3D. Also in video, if you think of instead of an additional spatial axis being the difference between frames, you have time that's playing out. And so that's the additional volume for some segmentation applications. And so to motivate this, I'll show you an example of brain tumor segmentation. That was work done by Jason Corso earlier. Following that, I'll give a more general introduction to just general segmentation and grouping in computer vision. I'll talk about video object segmentation, which is more work that I've done directly, where you're actually tracking objects throughout a video but the same mathematics applies to volume. And then also, at the very end, I'll show different medical applications using computer vision that I think are pretty cool. And some of this is from Tom Yan, the postdoc. Some of it is from collaborations that Jason has had with other universities as well. So in medical imaging, segmentation of anatomy and pathology is important, but it's also very difficult. So some of the difficulties I'll get to in a second, but you ideally want to be able to track volume, shape, and longitudinal variation in something like a tumor inside of a brain. Currently, that's a very manual, interactive process, and so the goal is to be able to automate this to some extent. So physicians and surgeons have more time to do other things rather than this very manual task. And then also be able to track data for treatment and analysis. Now, this is difficult because even if you have some kind of model for a tumor, it's going to be highly variable in appearance, size, and shape. You also have the pathology around the tumor is going to deform, which I'll get into in a little bit more detail. And this has been shown in prior work to actually be impossible to identify with simple thresholding type methods. And so you need a lot of different modalities, is the approach that Jason employed. And at the time that he was doing this work, there were really no biophysical models that were yet known. And the specific tumor I'll be talking about is, sorry if I get the pronunciation completely wrong, but glioblastoma multiforme brain tumor, or just GBM. And 40% of brain tumors across all ages are this type of cancer. And Jason was kind of explaining to me a bit, it actually grows so quickly that the interior of the tumor dies out. And so there's a surface area that's active and growing rapidly. Meanwhile, the interior of the tumor is actually kind of killing itself because it has no access to material. And then you also have this edema or inflamed area around the brain because this tumor is growing so quickly. So this is common, and it's also extremely fatal as far as the outcomes for patients who are diagnosed with this type of cancer. So here are two examples. These are manual kind of annotations of MRI data. And they're also T1 weighted and T2 weighted MRI images. I'm sure some people here know much more about the differences between these. But in some of them, the tumor is very apparent. And the T2, it seems like the edema is much easier to see. And so you can use both of these images in order to kind of segment out areas that you have from a scan as far as where is the tumor and where is this inflamed area for this live brain tissue. And so this is what an automatic segmentation using this kind of volumetric segmentation approach looks like. And so essentially we start with some initial image here. And what happens is we end up grouping pixels together based on the data that's available for them. So that's going to include both spatial information and, in the case of this image, some kind of intensity. And so you have these initial group of segments inside of this image. And this is also performed in a hierarchical manner, which is why we talk about this segmentation pyramid. And so what happens is not only are you grouping pixels together for these initial segments, on top of that, you can recursively segment those segments together. And when you do this recursively, you end up getting sometimes more meaningful segmentations. So you can see here at this level of the hierarchy, you pretty much have the tumor isolated. And the same is the case here. But eventually what happens is you get the higher and higher hierarchies. You end up kind of over-segmenting. And so now you're getting more area than just the tumor itself.
Is there an automated way that can pick the optimum? Or is that?
So there's some initial work on that. I'm not going to be talking about it here. But following some of this work of developing these processes, a previous student at Jason's came up with this hierarchy slicing method. And so he came up with some entropy definition, and he slices through these hierarchies in such a way that it's minimizing some energy function that he's defined for this. I think that is a very open challenge, though. And even for the method that I show, the different hierarchies give you different results. And kind of almost at an implementation level or the task that you're working on, it seems like the best way to deal with it is to leverage some additional information to inform which hierarchy is the most meaningful, or if you are going to span across hierarchies, you need like some additional information to kind of help you figure out which hierarchy is the most beneficial. But it is not even though this process is in place, it's been used in a lot of places.
So they may try feeding these into like learning.
Yes, that's done very often. And so in Jason's lab and in our group, a lot of people do working with images and feeding things in by 224 by 224, every single pixel, fine. That's easier to make some inference on than, say, a volume of video. And so oftentimes you can use something like this automated technique where you're going to be grouping things together as an initial processing step. And then this is the information that you're going to feed in. And it makes the number of parameters that you need for learning much more retractable, especially given the fact that, if you look at ImageNet, you have, about 1 million images that have been annotated. There's no such data set this large in video. And so anything you can do to make learning on video easier is like an active area of research as well. That's a good question. And by the way, if you guys have any questions at any point, please do ask questions. So I want to make sure that what I'm telling you is coming across and what you're more interested in as well. Here's just another example. So before we had a really good segmentation of the tumor itself, here what we find in the end is actually a very good segmentation, a higher level hierarchy of the edema area of the tumor. But again, because of this over-segmentation, the tumor kind of gets grouped in with the inflamed tissue. If you kind of follow this along, this may be like the optimal place as far as just segmenting out the tumor. But this is, again, it's kind of showing the weakness of this approach with what you brought up, that different hierarchies are good for different things. And so how do you sort that out? In the case of this brain tumor segmentation, I know that they use models specific to this task. So for example, if you had a model that described characteristics of the tumor, and you're trying to figure out if a neighboring segment was an edema, there would be a prior that would tell you, yes, like the segment next to what you're identifying as a tumor should be the edema, for example. And so he was able to leverage this information, and what you see in the end is these comparisons of manual segmentations of the tumor and the inflamed area and the automated process that was still kind of informed by the design of these models. But again, he's not manually going through and annotating these. And so there's some problems, like you can see here, there's this gap in the middle of the edema that like a manual annotation wouldn't have. But I think what's cool is, okay, so this is on the training set, but even on the testing set, I think he's even closer to the manual annotation of the tumor and the inflamed area. And he did develop a tool that can be used for this. And so you can actually have an MRI scan, apply the segmentation technique, and actively look through the different hierarchy levels, choose how transparent that overlay is with the image that you're working with, and then you can actually manually select some areas of that segmentation that you're interested in. And the thing I haven't talked about a lot is I've been showing you a lot of images, but keep in mind that there are slices that are involved here as well. And so when you select a supervoxel, which is a collection of pixels in 3D space, you actually end up with this 3D segmentation that you can help with in. So you're getting volumetric information by selecting these annotations on a 2D image. And more related to that is he also has done some work just identifying different structural elements from brain scans. And so I could not tell you what the function of these different areas of the brain are, but at this level of the segmentation, he was able to pick out some structures in the brain, as well as some finer, detailed, harder to find things like the hippocampus. And another thing you can do is, if you have this automated segmentation process, you can also do some post-processing with things like a graph shifts algorithm, which started originally in 2D, but can be applied in 3D as well. And so what you see here is there's been some initial segmentation of these different areas of the brain, and by applying this graph shift algorithm, it can go through and end up having a much cleaner result. That's actually much closer to the manual labeled example for this automated process. So that kind of concludes my trying to maybe convince you guys that segmentation does have some applications in medical imaging. I'm going to talk more about kind of the general segmentation method at this point. So does anyone have any guess what this object in the video might be?
Dog. Pig.
What's that?
Guinea pig.
Guinea pig? That's a very good guess.
Or dog. Dogs.
Did someone say
Dog.
dog? Yeah. So this is actually a dog. And in this case, as you get into the higher levels of the hierarchy, it becomes a bit easier to maybe kind of get a sense of that. And so the point of this is to kind of show that, okay, there must be some kind of encoding in this segmentation because you're able to pick out this object from it. And a lot of these are related to this space-time Gestalt principles. So the brain doesn't really process things, not pixel by pixel, but cone by cone. We actually group objects together, and that's how we kind of estimate and understand the scenes that we're observing. And so, for example, we have some idea of like space-time dynamics, right? So if I'm walking across this room, I'm not just going to suddenly be on the other side. So there's some continuity to these objects that we're tracking. Additionally, there should be a lot of pixels that are grouped together, because again, like my shirt consists of probably a lot of firing of these different cones in your eye, but they're being grouped together. So the idea is to segment these things together in a meaningful way, such that when you see this video that shouldn't make sense, you can still pick out things like this dog. Other important things are making sure that you preserve boundaries of objects. In the example of the tumor, we saw if we got to too high level of a hierarchy, we might start to segment the tumor with other areas of the brain. We also want to be able to do this in a way that's actually computationally feasible. So I'll talk about one variation of some of these general methods that's actually very efficient. And ideally, you don't have any more supervoxels than you need. So the dog was actually difficult to pick out when it had a lot of different segments for the same thing like the paw. So we do want to use as few superpixels as possible. So in the example I'm going to walk through, here's this video of someone snowboarding. And so we're going to represent this video V. And the idea is that we're going to form this lattice, gamma. And kind of like what I said towards the beginning of the talk, what we can do is we can actually line all these frames up where instead of having like a spatial Z dimension, each neighboring piece of the lattice is actually just another frame in time. From this, we need to define some segmentation, and we're going to minimize an energy function to do that given the volume. And I'll talk in 2 slides about some options you can use for the energy function. But essentially, you're going to have these segments that are differentiated by color in the output of the algorithm. And you can see that these reach across multiple frames as well as space within a single frame. Now, the other part of this is a hierarchical approach, which you've seen in the 2D sense. But essentially, we're going to recursively apply this algorithm, not just from a pixel level, but group these things together in 3D space. And if you keep applying this, you'll eventually get to the point where you really only have like 1 or 2 segments. And some of the assumptions of the model, basically, no segmentation is going to exist outside of the lattice. The union of the segmentation, the rest of the lattice is the lattice. And there's no overlapping between the segments. So they're completely disjoint, every segment. And yeah, as I've already kind of motivated, the hierarchical sense of this is not always clear, like which level of segmentation you should use. Like, so you can see here, there's this ladder in the background, and that still has some meaning in the low levels. But then as the dog becomes more meaningful, you actually end up losing most of the ladder. And so, again, with the edema or the tumor, depending on what level of information you're looking for, that kind of informs what level of the hierarchy is going to be most useful. But no single level at this point really contains the right information for the entire scene. So this idea of grouping pixels together based on some energy function has been around for a long time. And there are a lot of variants on how you do this. I don't know if you guys ever heard about graph cuts, but here's like the 3D version that was being used earlier, and brain tumor segmentation. This is a version of a minimum spanning forest that's more like what was shown on the previous slide. And I've also used this in a lot of work for video object segmentation. And then this is another method that I haven't heard about as much lately. So I'd say primarily these 2 methods are maybe the most successful. And the way that I can kind of say that in a meaningful way is because of this earlier work, libsvx. So a previous student of Jason's has basically built his ability to get a faculty job based on this work where he actually looked at all these different video segmentation methods and came up with some metrics for comparing them. And what he found was the method that used the minimum spanning tree was basically the most effective. And so if you look at accuracy here across the board, even if you get to the point where you have much fewer number of supervoxels compared to your initial segmentation, it still stays pretty accurate as far as maintaining the correct boundary. Whereas some of these other methods actually drop off pretty quickly. And then the more graph shifts and spire technique is just right here. So they have pretty similar performance, and I found the same thing in some work that I'll talk about that I've done later. But in addition to kind of evaluating all these methods, I think one thing that he found was if you have a really large video, this is actually very difficult to apply some of these segmentation techniques, because they create this entire lattice, and then you're grouping these pixels across this entire volume. Well, if you have an HD video that's greater than a minute or several minutes, this quickly blows up as far as a segmentation problem. And so they usually have to kind of divide and conquer, but then you have these very discrete, disjoint segmentation methods that are informed completely by the past. So he came up with a clever model that applies this temporal Markov assumption, where essentially what he's saying is, okay, so for our very first frame, we're going to group these pixels together, and this is the first level of our hierarchy. And then basically, because we have no previous frame, this is all we can do. So this is pretty much the same as like a hierarchical graph-based representation of an image. But then as I move to the next frame in the video, I can be informed by at least the previous frame on the same hierarchy level, as well as what's happening on the lower frame. And so by doing this, you can kind of keep this moving window of memory that's necessary. And so this isn't quite at the speed of real time. Sure, if you had enough computers, you can make it real time. But it's still computational feasible for videos of any kind of meaningful length of time. So you could have a 10-minute video, be processing on this. The amount of processing that you spend per frame is going to be the same regardless of the overall length of the video. And what happens is over time this does kind of converge on something meaningful, given that there's some movement in the video or something that's structurally there in the lattice that it can kind of glom onto. So all this is showing is that when you get to the next frame, you're just going to kind of shift this window. You're only ever using the very previous frame to inform the calculations that you're doing. And you're only ever using a segment below the current hierarchy that you're processing for. And here's an example of that segmentation method, just so you can see kind of qualitatively how well it does. This actually does a really good job at high levels of kind of segmenting out this snow border and maybe having some sense of the sky versus the ground. And certainly if you dive into some of the lower levels of the hierarchy, you're going to have less kind of boundary, I guess, cutting different pieces in together over segmenting, but it's kind of less informative on a per supervoxel level. And
you here assume that every frame has the same segment size?
well, so there ends up being some consistency, at least at each level of the hierarchy. But no matter what, the lowest level of the hierarchy in this approach, at least, is always just segmenting together the lowest level, which is the pixels. If you want to get into something that's combining the different areas of the hierarchy, you'd have to get into the entropy slicing paper. That's kind of a forward extension of this work, but I didn't include, but maybe I should have based on your guys' questions. Does that help? Okay. This is just an example of comparing, and what I was saying earlier about how videos have a lot of data in them, which is motivating the streaming process, and just looking at kind of a qualitative comparison of if you do things just frame by frame, in which case you're kind of violating the Gestalt idea of continuity from frame to frame. So you have a lot of jumping because these are all processed in isolation. You have this streaming technique, which has a finite amount of computation per frame and only processes each frame once, but satisfies this Gestalt time continuity because it's always being informed by the previous frame and trying to maintain boundaries according to that. And in this case, which I'm sure was cherry-picked, you have the version of the video that's actually segmenting based on the full video. And I think there are kind of more jumps here or a poorer segmentation. But in general, you do get a bit more performance on this, although you take a big hit as far as computational cost goes. Okay, so after introducing that, I want to talk a little bit about work that I've spent a lot more time on. So if you have more questions with this, it'll be much easier for me to answer. And full disclosure, I've only been a computer vision person for a little over a year. I actually did my PhD in control and dynamics and robotics. And what we had was a walking robot that had no eyes. And we could design robust control methods such that this robot was able to walk outside, walk over all kinds of terrain without being informed by that. But as a selfish roboticist, I figured if I look at a scenario like this, my robot would never be able to walk through here. Even though the terrain is not difficult, there are all these objects moving through the environment that it's unaware of. It's either going to run into this rail or this biker as it's walking through. Additionally, the sidewalk isn't that tough. There isn't much terrain variation that the controller can handle. But at the same time, how do you know you're not about to walk into a car? And so this is how I got interested in tracking objects in video. And if we look at this motivating example of having a car drive through, oftentimes a tool that people use to kind of inform understanding what's going on in a scene is they'll either use optical flow, which you're looking at the gradient of pixel intensities from frame to frame. And as a person, you can pick this out fairly well and you say, yeah, there's good agreement between this. But you're also getting things like artifacts of where this gradient in the concrete is moving, where the car has been. If you look at the overall optical flow, it's picking out the car well, but it's picking up a lot of other artifacts. Now, there's been other work in computer vision that's based on an individual frame, just roughly this category of visual saliency. And this particular example uses a lot of different visual saliency methods kind of together. And the goal of this is just given a single image, pick out the object that's most important in the image. And so for this problem of picking out the object, it does okay. But it also picks up maybe a lot of the building because maybe that stands out a bit more, being a yellow color. It also picks up a lot of this car here, which isn't even moving. So individually, each of these processing techniques has some flaws. The way that we got around this and come up with a meaningful way to combine these pieces of information together is what I'm going to call like distribution-based scaling. So if you look at the median deviation of optical flow, what you'll find is you know, in most videos, a lot of the objects are pretty close to the median. But ideally, if there's one object that kind of stands out as far as moving through a video or being an active object, it's going to have a spike that's kind of outside of this interquartile range. And so this is where we came up with what we're calling weighted saliency outliers. All it is taking Tukey's outlier test, coming up with a way of processing video through it, collecting how much of the intensities of either optical flow or visual saliency is actually outside of this interquartile range, and then based on how much of that data is identifiable as an outlier, scaling the data and saying, okay, we're catching on something that's an outlier, it's isolated in the video, this is a meaningful piece of data. Versus if you had something that had a lot of noise in it, you basically wouldn't use this source of information because you're not really catching on to anything that's an outlier or isolated. Everything kind of appears the same. Now, the motivation for using the difference from the median is just that if you have a video that's moving with an object that's moving, or if you have a video that's not moving and an object is moving through it, the median deviation of optical flow is going to be salient for that object. Meaning, if you're tracking an object, it's not going to have a lot of optical flow. It stays in the center of the camera, it's not really having a high gradient, but everything else is moving. So the majority of the pixels have high optical flow, so if you take the absolute value of that and look at the median, that vehicle that has basically no optical flow is actually fairly salient. And in the case that you have a camera that's not moving and the object is moving, you wouldn't have to necessarily do this median deviation, but it's robust to either case. So when we apply this, we have our original video, we have optical flow, and we have this combination of motion and visual saliency outliers. We're using these statistical measures to inform what we're tracking as a salient object, and we get much less artifacts. So basically where this car was being picked up before, because it doesn't really have a significant median deviation optical flow, it's kept out. Same thing with the street here. It's still there a little bit, but it's much more focused on the car as far as our confidence that this is the object that we care about in this video. Now, this was combined with supervoxels, or the kind of general volumetric segmentation technique. And the way that we use this information in combination is we had this initial estimate that was just based on these saliency outliers. Then based on a supervoxel that's through the whole volume, we actually formed a consensus on a supervoxel level. So we actually call this technique supervoxel gerrymandering. You can kind of think of it like voting. So basically, within a supervoxel, you have this measure of intensity of how salient is this object. You form a consensus. The nice thing is these supervoxels actually keep boundaries fairly well, even if they don't have as much information individually. And so this is what I was talking about using your application to inform how you should group supervoxels together. This is a picture of the foreground consensus. We also have a consensus of the background, and we can use that as a subtractive element. And now we're essentially left in this video without any human annotation, this object of the car being left out. And here's just a look at the process overall. We're going to tax the video card a bit here. But essentially you have your input video. In a parallel process, we generate the supervoxels for this video. From the motion and visual saliency outliers, we can combine these two elements together. We come up with a background consensus. So the black pixels here are things that we are saying are the background. The black pixels here are things that we are saying are the foreground. We can basically use the background consensus to subtract from some of the noise and this initial estimate. Then we have this refined approximation, and this is the output segmentation here. So the red area is what we're saying. This is the object that we're tracking in the video. Likewise, taxing the video card again. We can apply this to a lot of different cases. So before we had this car moving, here we have this dynamic object that's moving through a vehicle. So the object itself is deforming from frame to frame. And we're still able to track this fairly well, even though throughout this parkour video you had things like handrails that he was jumping over, occlusions as his legs were behind some object. Well, we're able to stick with this object from frame to frame throughout the video and converge fairly quickly. And there's a data set that we applied this to, the Davis 2016 Davis 2016 data set. And the whole point of this was just tracking the main object in a video for 50 different videos. And there are lots of different challenges that they had. Some videos you have problems where the object doesn't have a significant color difference. Some of the videos, the object is becoming occluded in different parts of the video, and so half of it's going to be on one side of a tree, the other half is going to be on another side. And basically the card measure is how much does your segmentation volume agree with the ground truth. And when we looked at this method we came up with, we essentially had the best unsupervised method for this Davis data set. And even with different variations of our algorithm, we still had first, second, third, and fourth place. And the next best algorithm was essentially in fifth compared to the work that we were doing. The other thing that we did was we used this as an opportunity to do kind of an arbitrage study on the different hierarchy levels to help with this question of which hierarchy levels are most informative. And what we found is, at least in this kind of case where we have additional information that we can use to group segments together, using the lowest level of the hierarchy where you had the best boundary kind of consistency with what the ground truth is, you would get the best performance. And then as you would get to the higher and higher levels of the hierarchy, eventually you would kind of drop off. Essentially because the supervoxels that you're trying to form this consensus on are grouping background and foreground objects together. The other thing that we found was that these complete video processing methods, where they process the entire lattice at the same time, do have better performance than the stream GBH version that I showed earlier. But this is still computationally much better in terms of being able to have an arbitrarily long video and being able to apply this technique.
So are you trying to pick out the object of interest? Right. Have you challenged it with like something that comes in, like another person walking by, and do you have something that does like persistence through the whole thing, or does it like all of a sudden switch to the other thing?
Yeah. So that can certainly happen. There are even examples in this data set. So here's just one where you have like a simple occlusion, for example. And you can see we actually drop this object a bit when we move through these trees, for example. But thankfully it picks the object back up. If you have other objects that are moving just as much as this one, it could be happening that during that occlusion it'll actually pick up this object as well. Because if you're already kind of dropping this object, you no longer have this kind of spatial temporal consistency constraint. And so you can glom onto a new object pretty easily.
Although if you had sort of a two-stage thing that could then look across a greater set of frames and say, this one's still here, and get rid of all the others.
So that's a great idea. And when we did the Supervoxel Consensus, that actually is processed using the stream GBH, but the supervoxels span across time. And so we actually look at supervoxels across the entire space. we come up with a feature vector that describes each supervoxel, which can be things like histogram gradients, LAB color space, RGB color space. There's really no limit on what features you use to describe these supervoxels. And then we use a local and a non-local consensus. So for example, if you have a supervoxel that in your initial estimate never was regarded as the object, but it looks almost identical in this feature space to all these other supervoxels that are being identified as this foreground object, it's still going to be included in this post-process version. And so that was kind of the trick. It's kind of the thing that you're talking about. You have this initial estimate, and then you go back and you refine it based on your findings over the whole video. It's similar to what Jason was doing earlier with graph shifts. He has this initial estimate, and then he's going back and refining it, minimizing some cost function. But when we did that, that's kind of what gave us the boost and the jump over all the other methods that have been applied before. And yeah, here's some examples of results that work well. Here's an example with more occlusions. But maybe here's an example that our method actually performs really poorly on. And we just cannot track this goat. It looks a lot like the rocks in terms of color. The rocks are actually just as salient as the goat when you're using the pure image-based visual saliency standard. And as far as optical flow goes, I mean, these rocks in the foreground are kind of moving around just as much as this goat.
But this is a case where you had, we're checking across the more, a bigger span of it. That's the only thing that would be common.
Here's the problem with this approach. If your initial estimate is so poor that you initially glommed onto something that was not the object, then your consensus is not the object as well. And so we actually get worse as we do this post-processing, because we're like, oh, it's definitely these supervoxels that look like rocks. And we're dropping areas that were originally segmented for the goat. Whereas some of these other techniques have used deep learning, and they have this idea of objectness. And that's been using things like ImageNet to train what these different objects are and being able to classify them. And you see that they perform very well in these cases. But at the same time, there are other cases where that really doesn't work, either because you're tracking an object that isn't necessarily well defined by your concept of objectness. Yeah, anyway, there are a lot of trade-offs depending on which approach you're using. I hope I didn't break the PowerPoint here. Here's a good example where objectness is actually very effective. You're not going to see the video moving, but just kind of use your imagination here. Each of these ripples of water have a higher gradient of optical flow than this duck standing still itself. So these tracking methods that were very reliant on where's a duck, where's a goat, where are these objects I've been trained on, does very well compared to our method. So in addition to your question too, this is about the Davis 2016 data set. Current work right now is dealing with the Davis 2017 data set, which we did add some new kind of manually, how do I want to describe this? Like kind of trying to find more manual techniques of making meaningful information from this data. And all first through fifth place was all deep learning based methods, right? So people are just throwing all this information into a neural network and then training it. It doesn't matter if they understand the difference between ground truth or not. This network can work while you're sleeping, it will figure it out. And Davis 2017 actually has a bit more challenge because it's actually tracking in one video, say 7 different dolphins moving through water. I can't tell one dolphin from another. So these dolphins are moving amongst each other, and there are some of these techniques that we're able to figure out and track an individual dolphin moving through, even though it's occluded by other dolphins, and then taking back up on it later. So there are definitely more challenging example videos that are quickly ramping up, and the community is getting more behind. But in general, from what I've seen in computer vision, the video is often like an afterthought, and now more and more people are becoming interested in it. You're also seeing in media, more and more people are using things like video as opposed to just messaging, I guess taking photos or something like that. And it's actually related to some work that I'm doing with DARPA, where we're trying to create manipulation videos. And what they want to be able to do is automatically detect if an image or a video has been manipulated. And right now the results in the image space of that are very good, but video is almost nowhere. So we're creating these manipulated videos, but there's really no way you can detect them anyway, regardless of how good of a job that we do manipulating them. So Anyway, point being just that it's nice because this Davis data set just started in 2016, and already in 2017 you see a lot of ramping up in the difficulty and the results that people are able to achieve on that. So I think what we'll see in the near future is a lot better computer vision techniques in video. And in some cases that's way far behind, but in a case like this video object segmentation, like we're right in the middle of it ramping up as an active area of research and getting a lot of new results.
Are you limited to doing it in the forward direction?
No.
Does anything become easier in some
Yeah.
cases if you go backwards?
Yeah, so this is perfect for some work that I've done related to that, because with this object tracking, you can have a user input just say a bounding box, and then pick a frame that they do that, and then you erase this object from video. Now, if you have a good segmentation of the object moving through space, there's another really smart guy who's figured out how to inpate even dynamic objects like waves behind an object, and to some extent even people moving behind an object. And so what we need to do is come up with a really good segmentation. Now, one problem that we had early on was this only forward-thinking type process, because we would track that object from the initial frame and then move forward. But oftentimes, you might have an object that you're trying to remove from a video completely, and initially, that object isn't much in view. So the segmentation that you have available at that point is very poor. So initially, your removal of this object is really bad until this person almost moves completely into the video, and then you can start tracking with it really well. They get removed really well. Well, the paradigm shift was, well, let's annotate this person in the middle, and then let's propagate this technique forward and backwards. Our initial estimate got very good, and then the post-processing then also was more informed. Now, you could probably come up with some way to do this iteratively and have like more processing of forward backwards. We just did it kind of a naive way. We ran our algorithm this direction and this direction from here. Just kind of depends on to what extent you're willing to code it up and then how much time you have computationally.
Get more grad students.
But I think that'd be applicable to like the tumor example as well. Like maybe you could do reprocessing of the volume of where the tumor is if you had an intermediate and kind of somewhere close to the endpoint annotation, and then you just filled in the area in between. And then you wouldn't need to go through and manually annotate, and you'd have a fairly well-informed process for getting the entire volume accurately. I'm going to talk a little bit about Tom Yan's work. So he was using segmentation in a way where they actually had these rainbow images, and the goal was you have these pictures that are kind of outlining these different neurons in the brain and their different connections. Is there a way that we can track these connections from frame to frame? And the way that he did this, can't have a computer vision talk without talking about deep learning, but is using deep learning based techniques where essentially they had these slices of images that were from this brain scan. They would apply this pre-trained denoising technique and then use a tri-layer LSTM, which I'll talk a little bit in 2 slides. And then the output is essentially having this actual 3D volume where you're identifying these different neurons and then their connections throughout these different slices. So this is just talking a bit about this pre-trained network. I don't know how many people here use neural networks. They're very popular in my lab. I've been hesitant to use them to some extent because I believe in human intelligence instead of computer intelligence. But after getting the floor wiped in the Davis 2017 challenge, I'm now drinking the Kool-Aid as well. But one thing that's nice is people have a lot of these networks and their weights are available. So you can do things like grab this VBM 4D network that someone else has trained and has got really good performance on. You can almost just drop it into the problem that you're working on. And so this is something that we're doing to make our segmentation better. We're actually using some of these pre-trained networks as opposed to classifying things as a cat or a dog. We're sticking to the high-level feature space that's like a vector of 4,096 different values, and then using that to come up with these descriptions of supervoxels as opposed to things just like RGB, LAB color space, things that we can think of manually.
They have a pre-trained model. Is that set for a specific image size?
Yeah, so part of what you have to do is kind of pre-process images and figure out a way to take what you're dealing with in your problem and force it to work with this other network.
So if you all of a sudden wanted to do like a higher res,
Yeah.
a lot more pixels, you'd be kind of...
But the other thing you can do too, though, is you can add intermediate networks that kind of take care of the process of transforming your input data that's not the right format to the correct format. So you maybe have 4 layers that do this. You train on that problem, given some output classification. you're only dealing with weights associated with 4 layers. You're still leveraging these other 16 layers or more of the network someone else trained. You can just freeze those. So there are ways that you can use deep learning to deal with that problem as well. In my case, I'm just manually picking out these segments, reforming them to be the correct space, and taking out the mean difference for the areas that are not the segment for the input space. So if you have a segment, a supervoxel, for example, that in one slice is 100 pixels by 100 pixels, but your input is 224 by 224, essentially the non-segment area is being colored as close as possible to what's considered invisible by the network. Because usually what they do as a pre-processing technique is minus, let's say, the mean RGB value of their entire training set. So that value is essentially invisible to the network. So there are manual tricks you can use, and then there are also like these principled deep learning ways that you can transform your data to work for another previously trained network. Just to beat the dead horse a little bit more, you can have the same input, and if you're just trying to do a different classification problem, just train the last layers are actually taking the output vector and translating it to these classifications that you've kind of defined in advance. Yeah.
Just wanted to add that for most commonly used CNNs, pre-trained networks, the way convolution works, they don't care about the image size that you fit in. The only limitation that you have in the network on the input size is fully connected layers or average pooling that you can have at the bottom. So if, as you said, if you chop that off, the convolutional part doesn't care what the size of the image you fit it. Even if it was trained on like 244 by 244 in the ImageNet originally, and you have 600 by 600, as you remove the fully connected layers in the end, it will take 600 no problem, and will apply all of those things. And then you can have your own classifier in the end, or some kind of adaptive average pooling at the bottom that doesn't care again about the sizes. So that's used a lot. Another trick that people do, instead of if you have the set images that you're new set of images that you're fine-tuning on, and it's different from the ImageNet, different from the original ones, people just before the network they stick in a couple of normalizing layers that also learn like batch normalization before the rest of the network, and then it starts sort of learning how to normalize the new data set that you fit in. So there are a couple of tricks that I think pretty widely used now. But yeah.
This is really good. We have a local deep learning expert, which I am not. But yeah, I guess maybe one of the most common layers is the convolutional layer, which is part of the, I guess, denoising network that he was using, along with some of the other features. Because we kind of talked about deep learning, I won't go into the details of this as much as LSTM. The difference with LSTM is you're essentially taking input data from multiple time steps, which is really useful in video, or in this case, the Rainbow project, where you have slices of these images spatially across like the z-axis. And so now the output of this network becomes based on not just the current image, the current slice, but multiple slices that you were processing before. And Tom Yan actually applied this using 3 layers of these LSTMs. And when you look at the overall output, it seems like, at least qualitatively, they got pretty good segmentation of these objects in the volume, these very small neurons, through these rainbow images. And then here's an example, too, where you have the raw image, and then these different red dots are actually all of the connections associated with this neuron here. And if you're interested in this work, definitely feel free to check this out, and I can get you the name of the paper, too, after the talk as well. Another thing that Tom Yan has done is looking at where you have these multiple channels and some kind of like chemifluorescence imaging application, and trying to unmix them so they can be more meaningful in images. I think he just used kind of a k-means classification to do this, but maybe some of these are a little more apparent than others, where before maybe there was less distinction between these 2 channels, but by using this unmixing process, he's able to take data for specific channels and make them much more visible in an image that a person could look at. And then back to some of the work that Jason's had. They've looked at when you have a camera available and you're performing surgery. Sorry to show this with pizza. They can do things like try to automatically identify based on where they know these different tools are. if there's bleeding going on, these different things of classifying these activities during a surgical operation. And this is just way out there, but I actually saw Siskin come and give a talk, and somehow this is real. But what they do is they play a video for a person in an MRI, and then based on their brain scan, a network predicts what the person is looking at. So you're talking about video processing where you're not even processing the video, you're literally processing a brain scan of a person that's watching the video. And it's able to do better than these networks that were trained to process the video into like the semantic description of the object. So anyway, definitely check that out if that's something that's of interest to you. I'd just like to one more time thank Tom Yang and Jason for sharing some of those slides, and sponsors who supported this work as well. And I'm happy to answer any remaining questions that you guys might have. You guys did a good job of asking questions during the presentation. So
are you working on medical segmentation as well, or just natural images?
No, not at all.
Okay.
The stuff I'm working on has actually gone from more of the video object segmentation that I presented on towards the middle, towards using perception to inform actions that a robot takes performing some task. So I'm still very much a roboticist that has jumped into computer vision, like I said, for selfish reasons of recognizing limitations of just being a controls guy, trying to do a lot of different automation tasks.
Right.
You need something to actually inform what's going on in your environment. And
well, that's a pretty popular task right now, especially with the self-driving cars, autonomous driving perception for them. They're basically essentially doing the same, right? You have a camera and then you have the flow of the input and different objects that you want to avoid or take the road and turn in a pedestrian. So I think that's pretty hot area and a good data sets too, like Muskogo and the Pascal Log and some other ones that are widely used. So a lot of pre-trained models for you guys.
the thing I'm really excited about too, because of automated vehicles, is it seems pretty clear to me that big car companies are like bought into this idea that it's going to happen, and you don't want to be beat. You don't want to be the last manufacturer to have these. And I think the other cool thing that seems to be recognized by potentially Ford, but especially like Toyota or even Honda early on, but I think now that you have more companies making these competitive investments, is they're recognizing once we solve all these problems for automated vehicles, here we have all this technology that can now be applied to things like home service robots. So you actually have these companies that are willing to fund these projects and take them seriously that maybe before there were less opportunities for it. So that's also the reason why I'm able to work on these other kind of perception and directly tied to robotics projects that are funded by the same people doing like automated vehicles at the same time. So yeah, I'm like a little kid when it comes to robots. Like I'm just very excited about them. So like compared to when I started my PhD, it's like, what the heck am I going to do following walking robot work? It's like, oh, like people are recognizing some value like in industry. So this may actually take off. But all right. Well, thank you guys.
Thank you.